To remind you where we are, we're in the thick of a bunch of stuff here, so I've summarized it on the board. In the first place, I can use a pointer. We're considering a case in which there is a potential that's rising as you go to the right, so that there's a classically allowed region to the left of the turning point and a classically forbidden region, CFR, to the right. These are also labeled 1 and 2. XR here is the turning point itself, and the R just means that this turning point is to the right of the classically allowed region. Down here is the face of the picture. Then, using the WKB solutions that we've worked out so far, in the classically allowed region, which is region number 1, the momentum function is defined like this. It's a real function, real and positive function. The action function, or the function S, which appears in the exponents, also called an action, is basically the integral of p dx. Here's a question of the lower limit, which, as I pointed out last time, is related to the phase convention of the wave function. So you can set it for anything for now. More about phase conventions later. The most obvious point to choose is the turning point itself. And that's what I've done in this integral here. And I've called it S of x comma xr to indicate what the lower limit of integration is, to be explicit about that. In any case, using a linear combination of the forward and backward, or right and left going solutions, either the IS and either minus IS, or their H bar, with coefficients C right and C left. This gives us a general linear combination in the classically allowed region. Now, in the classically forbidden region, which is also labeled number 2 here, the momentum is purely imaginary. If I take its absolute value, it just means to drop the I and just deal with this positive square root. And we define a modified action we call K, which is the integral of this square root dx, absolute value of p of x dx. And again, the lower limit is based on, it really determines normalization in phase of the wave function. And just to make it definite, so we have a definite number, we'll use, again, the right turning point xr here as the lower limit. And then we form a linear combination with the 2 WKB solutions, a growing one and a damping one, with coefficients C growing and C damping. And so we have these 2 solutions in these 2 different regions, and in each region there's 2 arbitrary coefficients. Now the problem is to connect together the C right and C left in the classically allowed region with the C growing and C damped in the classically forbidden region. But as I explained last time, you can't do that just by bringing in both solutions up to the turning point, because there's a certain region around the turning point where both these solutions become invalid. Let me elaborate on that breakdown near the turning point just a little bit. I'll cover this up and we'll bring it back again. As you'll recall, the amplitude is the amplitude squared times the velocity is the same as the amplitude squared is the same as the classical probability density, which is proportional to 1 over the velocity v. This gives the amplitude is proportional to 1 over the square root of the velocity, which is proportional to 1 over the square root of the momentum, which is how it's appearing in our formulas. In any case, if we have a situation like I sketched a moment ago, where we've got a turning point that goes up like this, here's the energy E. Then if we plot the velocity, you see the velocity is positive here, but then it goes to 0 as you come to the turning point. So 1 over the velocity, or 1 over the square root of the velocity, is going to be a function that's going to do this. It's going to diverge at the turning point. In fact, you can see that the divergence goes as, well, the divergence goes, the amplitude A goes as 1 over the square root of the velocity, it goes to infinity there. Also, as I explained last time, this implies that the conditions of the WKB approximation, which is that the wavelength should be much less than scaling, breaks down there, because near the turning point, lambda actually goes to infinity, since the momentum is going to 0. Okay, so no wonder the WKB solutions don't work there. But there's you might say the nominal WKB solution blows up at the turning point. It does also in the classically forbidden region, because there's a 1 over square root of momentum there as well. They both blow up at the same place. Now you might ask, what does the real solution do? What does the real quantum mechanics do? Well, by the way, the classical probability is a meaningful quantity classically, and it does diverge there. It diverges as 1 over the square root of the distance from the turning point, which means that the integral of the classical probability is finite, as you'd expect, since it's a probability which can, for an oscillator, a bound state system, you can normalize. And that means the amplitude actually goes as 1 over the distance to the 1/4 power from the turning point itself. But they diverge, and so there's a question about what does the real wave function look like? Does it diverge? No, it doesn't. It's a solution to the Schrodinger equation. I'll show you in a minute what it actually looks like there. But in any case, that's the problem near the turning point. And we fixed it up by inventing yet a third solution, again an approximate solution, which is valid in the immediate neighborhood of the turning point. We do this by approximating the potential by a straight line there. If I draw it in, it looks like this. This is going to be valid at least in some region around the turning point. Here's a series of the potential carried to first order. XR is the turning point. This is just a constant coefficient here. It's the slope of the potential. If you plug it into the Schrodinger equation, it becomes this. It's now a Schrodinger equation naturally with linear potential because that's what you replace the real potential by. And as I explained last time, we'll clean this equation up by doing a linear transformation, going from an old variable x over to a new variable z, such that z equals 0 at the turning point. So over here, in this diagram here, this classically allowed region is the one where z is less than 0, and the classically forbidden region is the one where z is positive, and the turning point itself is z equals 0. And the constant a of the transformation, we choose to clean up the physical constants in the Schrodinger equation, and this turns out to be the choice that does it. And if you do it, you end up with a differential equation for the wave function in the neighborhood of the turning point, which does not involve any constants at all. It's now a completely dimensionless form. And this, as I explained last time, is the standard equation for the area and vary function, which are special functions. These are the two linearly independent solutions of this equation. And so in the neighborhood of the turning point, the wave function is now a linear combination with a coefficient area and a coefficient vary of these two functions, area and vary. And as a result, we now have three different regions with three solutions. In each solution, there's two pairs of coefficients. So there has to be a connection, now 6 coefficients altogether. There's got to be connections amongst these coefficients, which we need to work out. Okay, so how do we do this? Well, before I do that, let me tell you about the area and vary functions. I'll unfortunately have to cover this up, but if you go to the books on standard functions, special functions, you'll find under the chapter on the area and vary functions, you'll find these limiting forms for these two functions when z is large and negative or when it's large and positive. And this is just what you get out of the books. I could derive these formulas for you. It's actually not that hard. Take about a lecture or a lecture and a half. But for lack of time, I won't do that. Let's just say we read it out of the books. But what you can recognize is that these are asymptotic forms valid in large and small z. What you can recognize is that there actually are WKB forms. You see, in the classically allowed region, which is z negative, you've got cosine and sine terms. These are real exponentials of two waves going in the two directions. And in the classically forbidden region, you've got growing and damping exponentials. So that part's easy to see. In order to understand these formulas, however, let's adopt a physical model in which the potential really is a linear function of position. An example would be, let's say, V of z. Let's say a particle in a gravitational field where the potential is mgz. Then the Schrodinger equation is, of course, minus h bar squared over 2m. And also, let's take the energy equal to 0. Let's do that. So it's minus h bar squared over 2m. You have d squared psi dz squared plus mgz psi equals 0. You may compare that to the area and vary equations, which is right here. And you see, except for the constants, it's the same equation. So, apart from scaling and constants, the area and vary functions are the exact solution of the Schrodinger equation for a particle in a gravitational field with a zero energy. Let's look at that problem from the standpoint of classical mechanics, or maybe you might say WKB theory. So here's the z-axis, and so you imagine the particle is climbing in a gravitational field. The total energy is 0, so it reaches a turning point at z equals 0, and then turns around and comes back. So as it climbs in the gravitational field, of course, its velocity decreases, it's decelerating. That means the momentum is decreasing, and that means the wavelength, which starts out short, gets longer and longer and longer as it comes closer and closer to the turning point. Also, since the velocity is going down, it means the amplitude must be going up because, as we just have learned, the amplitude goes as 1 over the square root of the velocity. So just on general WKB grounds, we expect a kind of an envelope that looks like this. Then there's going to be oscillations in here, and as you move further towards the origin, the wavelength gets longer. And finally, what it does is it does something like that. It doesn't go to infinity, but it reaches a maximum near z equals 0. That's the turning point. And then there's some penetration into the classically forbidden region where the classical particle wouldn't go at all, positive z, and you get a decay over here, an exponential decay. Well, this is actually a sketch, not a bad sketch, if I do say so myself, of the area function AIZ, which you can look it up in the books. But this is a way of interpreting what that solution means. Now, as far as the Berry function is concerned, that's the other linearly independent solution, and it also has the same envelope, like this, but the oscillations are 90 degrees out of phase from the area function, so I can't really draw them on the board, but they get longer wavelength as you get closer to z equals 0. And then what happens is in the classically forbidden region, they diverge exponentially. And this is the Berry function, which you would say is the solution that has to be rejected because of boundary conditions for the particle in the gravitational field. But nevertheless, it gives you, again, I say by this physical model, it gives you an idea of what these asymptotic forms mean. And carrying these exact solutions out to large negative z or large positive z for both these functions yields these expressions we have here summarized over here for you, copied out of the book. All right, so that's the properties of the area and Berry functions. It's not so bad, actually. So now, if I may reveal my board again here, it must be that these WKB solutions, psi1 and psi2, which you see here, must be the same with coefficients CA and CB, C area and C Berry, the same as we get by taking linear combinations of these asymptotic forms. So, for example, if I look at the classically forbidden region first, which is where z is positive, then this exponent which occurs in our WKB solution here, which is k of x comma xr over h bar, must be equal to that exponent beta of z up there. Well, let's see if it is. Let's show that it is. It turns out it is. Here's what I'll do. So the exponent in these asymptotic form here, beta of z, which is equal to, as you see, it's 2/3 of z to the 3/2. This must be equal to, I'll put a question mark on it because we want to verify it, 1 over h bar of k of x comma xr, k evaluated relative to the turning point. In the first place, they both vanish at the turning point, so that's what lets me know that this has to be xr on the right-hand side. Now this is, if I, to check and see if this is true, let's plug in the definition of k. This is the integral from xr to x of the square root of twice the mass times the potential energy v of x minus e dx. Now we use the approximation we use to get the area function, and replacing the potential energy v of x by v of x at the turning point plus x minus x at the turning point times v prime at the turning point. That's just the first two terms of the Taylor series expansion. And if you do that, then the energy E cancels the v of xr because the energy is equal to the potential at the turning point. That's the definition of the turning point. And the result is just this term is linear in x minus xr times a constant. So this turns into, if I take out the constants, it's 1 over h bar, the square root of 2m times v prime of xr. And then we've got the integral from xr to x of x minus xr to the 1/2 power dx. These should really be prime x. This is where I want to be careful about distinguishing the variable of integration from the upper limit. But anyway, that's the integral we get in this straight line approximation. And this integral is easy to do. It gives you 3/2 x minus xr, excuse me, it's 2/3 of x minus xr to the 3/2 power. And that's nice because, first place, we see the 2/3 appearing, and we see where it came from. And we, as far as the z to the 3/2, which appears in the math books, we're getting x minus xr to the 3/2. But our linear transformation is that x minus xr was this quantity a times z, so this is az to the 3/2 power. So that's a to the 3/2 times z to the 3/2. And so the z to the 3/2 that came out of the math book is appearing in our integral here. There it is. And so the only thing that's left over is to show that these remaining constants here, which is this thing, times a to the 3/2 gives us 1. Well, if you go back to the definition of a, which is buried in the board here it is. I remember what it is, so I'll copy and charge it. It is h bar squared over 2m v prime x of r, that whole thing to the 1/3 power. That's the a, but we need to raise that to the 3/2 power. And you see it gives overall 1/2 of the square root. Therefore, the square root of h bar squared cancels h bar, square root of 2m v prime cancels that. The whole thing works out, and this thing is verified. This is indeed true. These exponents are the same. So this exponent of negative z is the same as the exponent 1 over h bar k for one of our two solutions in the classically forbidden region. Now, what about the amplitude? We've got 1 over z to the 1/4 here for the amplitude that came out of the math book. How does that compare to the amplitude of our WKB formula? We can't expect them to be exactly the same because there's constant multiplicative constants, but they certainly should be proportional. So our amplitude in the WKB formula is 1 over the absolute value of p of x, square root of that. But that's 1 over the square root of p of x. The absolute value of p of x is the same as this square root here. Let me do it this way. Let me just concentrate on p of x itself. Absolute value of p of x is equal to this square root. But in this linear approximation, you see it becomes equal to the square root of 2m times v prime of xr times x minus xr. But x minus xr is the same thing as a times z. And so the whole thing becomes proportional to z to the 1/2 power. You can see here just the square root of z. And, but this is not the amplitude. What actually appears in the amplitude is the square root of this down in the denominator. So what we get is the square root of the absolute value of p of x. That is proportional to z to the 1/4 power. And that's exactly what comes out of the math books, z to the 1/4. So these are really, these asymptotic forms that appear in the math books are really WKB solutions. They don't tell you that, but that's what they are. Okay, so the only thing that's left over to match these solutions together is just the constants. You just need to work out what the relation is between the coefficients that multiply these solutions. And so that's entirely straightforward to put that together. And I'll just summarize what you get when you do that. Maybe this is a good place to do it, because you find that the damping and the growing coefficients, C damping and C growing, are equal to the square root of h bar over pi times a, where a is that tiny constant, multiplying with 1/2 of C area on top and then C area on the bottom. This is just a translation between these two types of coefficients that we get by doing that. All right. So this final formula here that I've written down basically connects us from the turning point region over to the classically forbidden region, and connects this solution number 2 here with this area and vary solution over here. To finish things, we need to go the other way as well. We need to connect the turning point region with the classically allowed region. And this is done in exactly the same manner as I just outlined. That is to say, we first start by looking at this exponent s and seeing how it relates to our function alpha up there. And if you go through the same type of analysis, just use a linear approximation for the potential and do the integral, you'll find that they're the same, except for one thing, which is that pi over 4 up there. In fact, you can see that has to be because if I evaluate alpha at the turning point, which is z equals 0, then it's equal to pi over 4. Whereas, if I evaluate the function s of xxr at the turning point, it's the integral is 0, so the answer is 0. So they're the same except for that additive constant. Now to fix that up, I'm going to do something here, which is just amounts to a redefinition of these coefficients CR and CL. Allow me to add an I pi over 4 to this form here, and over here I'll subtract an I pi over 4. And all that really does is amount to absorbing or removing a factor of e to the I pi over 4 from the CR and CL. And it just simplifies the algebra somewhat. And if you do that, then it now becomes easy to find the connection between the right and left coefficients and the area and vary coefficients. And range like this. We get CR and CL is equal to the wrong piece of paper here. The wrong piece of paper, this is the one, is equal to 1/2 of this same square root h bar over pi a. And then what we get is C area minus IC vary on top and C area plus IC vary on the bottom. We probably aren't so interested in the area and variance coefficients. We're really interested in the right and left and the growing and the damped. And if we put those together, just by eliminating the area and vary coefficients in this, we can find connections between the right and left and the growing and damped coefficients. And if we do this, then I need to go on to the next page. And here's what we get. Is we get C right, C left is equal to this matrix, which is minus I over 2, and I over 2 here, and then a 1 and a 1, multiplying C growing and C damped. And for reference, I'll write down the inverse of this, C growing and C damped, and take the inverse of that 2 by 2 matrix. And this becomes I minus I, 1/2, 1/2, multiplying onto C right and C left. And these final matrices are the main result of this immediate stage of calculation. These are what are called the connection rules, because they allow you to connect together the WKB solutions in the two regions of the classically allowed and classically forbidden, having gone through this intermediary of area and vary, which now drops out because we have eliminated those coefficients. All right, so that's the main result of this. Now, having gotten those connection rules, let me now apply them to a practical problem. Let's see, the main diagram I want to show you is right here. This is still the same picture we use here. Let's consider a case where we have a potential that rises like this, and say it never comes back down again. And you're doing a scattering. It's a one-dimensional scattering problem. You send in a wave like this. It goes in. There's an incident wave. It hits this potential barrier, reflects, and comes back out and gives us a reflected wave going like this. Now, at large negative x here, this potential goes to 0, so it's really free particles. This is typical in scattering situations because you launch your particle in a region that's far away from where the potential is active. This is only 1D. But anyway, the general solution is going to be obviously a linear combination of the incoming wave and the reflected wave. And that's exactly these two waves here, the right and left going wave. That's what they are. So let's analyze this problem and see what the solution to the Schrodinger equation is. Well, the way to do it is to use the connection rules. Erase this stuff here. And I'll go back to the whiteboard here. In the first place, in the classically forbidden region, which is over here, the wave function has to be dying out, has to be damping out. We can't have it blowing up because it would diverge at infinity, and that doesn't satisfy the boundary conditions. Besides, it's in the classically forbidden region, it's got to be damping. And as a result of these two coefficients growing and damping, the growing coefficient must be 0. And as for the damping coefficient, which is the only one that's left, also, all right, so then I can erase this here. And as far as the damping coefficient, which is the only one that's left, you can see it's equivalent to a normalization in phase of psi. So let's just take the damping coefficient equal to 1. We can renormalize it later on if you want to, but just 1 will work for now. So on the basis of boundary conditions, what we do is we say that C growing is 0 and C damping is equal to 1. Now then, by this matrix right here, this connection rule, we just do the multiplication, and what this shows us is that C right is equal to C left is equal to 1. Which you've got a damping is 1 down. This is 0, 1. This vector equals 0, 1. Multiply it out, this is what you get. And the result is that we find that psi in region 1 of x is 1 over the square root of p of x. And then what we have is e to the I s of x comma xr over h bar plus I pi over 4 plus e to the, really plus the complex conjugate, because the second term is the complex conjugate of the first. And we also get the solution in region 2. It's 1 over the square root of the absolute value of p of x, which is real in that region, times e to the minus k of x comma xr over h bar. All right? We're probably mainly interested in the solution in the classically allowed region because that's where the particle is launched from, is large negative x. You send particles in and they come back. So let's look at this solution here. In the first place, you can see that the solution is real because it's the sum of the term and its complex conjugate. In fact, it can be written as 2 over p of x times the cosine of s of x comma xr over h bar plus pi over 4. There's a couple of lessons in this. This is a simple problem. There's a couple of lessons in it. In the first place, there's no quantization of energy. There's nothing in the solution that requires that the energy take on any particular value. That's because we're in the unbound positive energy. It's in the unbound spectrum. It's unbound states, and so it's a continuous spectrum. The energy can range from 0 to infinity in a problem like this. Second thing to notice is that the solution is, there's only one solution we obtain. The solution, in other words, is non-degenerate. Now recall I argued or I showed you that in one-dimensional problems, if the wave function is forced to go to 0 at either one or the other of the infinities, or even at a hard wall, it doesn't have to be infinity, then the solutions are non-degenerate, and that's just what we see here. Another point that I made was that in one dimension, the non-degenerate energy eigenfunctions can be chosen to be real. That is to say, if they come out complex, it's only because they're multiplied by some overall complex number. And indeed, we see this as real. Yes?
When you write that line, where you replace the exponential with the cosine,
yes.
Is that p of the x, or is that the square root?
Excuse me, yes, it's the square root of p of x. Thank you. Is that what you're asking?
Yeah.
Yeah, square root of p of x. So anyway, all these features of these one-dimensional problems that I mentioned are revealing themselves here. Allow me to write this. I want to extract as many lessons as I can out of the scattering problem. There's several interesting things. Allow me to write the solution in a slightly different way by factoring out an e to the I pi over 4. This is just a trivial change. E to the I pi over 4. This is an overall phase factor naturally, divided by the square root of p of x. And then what's left over is e to the I over h bar s of x comma xr. This is the right traveling wave. And then we write the left traveling wave as a coefficient r times e to the minus I s of x comma xr over h bar. And r here is, by factoring out e to the I pi over 4, there was an e to the minus I pi over 4 up here. But that goes into minus pi over 2 when I factor this factor out. And so r is equal to e to the minus I pi over 2, which is the same thing as minus I. It's a pure phase factor. Now, the idea here is that this is the incident wave that we send in, and here's the reflected wave coming back, but the reflected wave is multiplied by a coefficient complex number. And this complex number is called the reflection amplitude. Definition of it. And so as I say, it's just the multiplicative factor giving you the reflected wave. There's something that comes up in a minute which I'll call capital R, which is the square of the reflection amplitude, and this is called the reflection probability. which in this case, since the reflection amplitude is a phase factor, is just equal to 1. Now, the fact that the reflection probability is equal to 1 means physically that since this barrier goes up to infinity, that any particle that hits the barrier must bounce back. And so therefore, the probability of getting a particle back where you came from is 1. All the particles have to come back. There's no possibility of penetrating the barrier and coming out to another side somewhere. There's no tunneling here. This goes on up forever. All right. We can understand these reflection amplitudes and probabilities a little better from the standpoint of fluxes. So let me remind you of some things about fluxes, which I spoke of in the last lecture. And I'm completely out of chalk except for tiny bitty pieces here. In the first place, the continuity equation in one dimension says that d rho dt plus dj dx is equal to 0. But this is a time-independent problem, so everything is the density in particular is independent of time, so is j. So this term drops out, and it just turns into dj dx equals 0. Or to say that j as a function of x is actually a constant, it's independent of x. However, j's definition is that it's psi star times minus ih bar over the mass m dx applied to psi, and it's not quite that. J is equal to the real part of this. This is the probability flux in one-dimensional problem. Now, we have two waves here, an incident wave and a reflected wave, and we can compute the flux of those two things separately. If we compute this for the incident wave, what do you get? Well, parentheses around that. What do you get? Well, the ddx brings down a derivative of the phase s, which is s prime. But the psi star psi is going to involve the square of the amplitude, which is 1 over the square root of p of x, and so that turns into a p. And the combination of those is equal to 1 because p is equal to s prime. And in fact, what you find is that it's only this mass term is the only thing that survives. You find the incident flux of 1 over m, and sure enough, it's independent of x, as it has to be. Anyway, this is what it is. Now, what about the reflected flux? In this problem, as I just showed, the reflection amplitude is a phase factor, so its square is 1. But let's consider maybe we have a more general problem where r is any complex number. If you go through the same calculation, you'll find that this is equal to the absolute value of r squared divided by m, which is equal to capital R times the incident flux. So this is why capital R is called the reflection probability. In effect, it's the probability that a particle which is sent in will be reflected. And this square of this r is always going to be less than or equal to 1. It's equal to 1 in this very simple case. All right. Now, so that's the lesson about reflection of amplitudes and probabilities. There's yet another lesson that I would like to make regarding this very simple solution, and it goes back to this phase-based picture of the motion of the particle. Maybe I have enough room to say what I need to say here. The action function s, it's called an action, it's divided by h bar, it's the phase of the wave function, is basically the integral of p dx. That's the definition of it. Now, a useful way of thinking about this action function is to imagine that as the classical particle is going around the orbit as a function of time, it carries a little integrator with it, and it knows what its momentum and position are, and it just integrates this as a function of time to create a function, let's call it s of t, as a function of time along the orbit, and that's equal to the integral of the final time t of the momentum as a function of time times dx dt, which of course is the velocity as a function of time, dt. It's the same integral, but just expressed with time as an independent variable. So let's say our particle carries an integrator like this. For this kind of a problem, let's choose t equals 0 to be the turning point itself, and let's take the lower limit of this integral to be 0, so just to get a definite lower limit. Now, when you're in the upper half of this orbit here, the momentum is positive, and the dx is positive too because you're moving forward. So that means that s is increasing on this part of the orbit. When you get to t equals 0, then you go down this way, going this way. Now momentum is negative. But the dx is negative also. And so s is still increasing. And if you actually plot s of t as a function of time, it looks like this. It's actually negative. In negative time, it kind of goes like that. Anyway, the point is it's increasing everywhere. On the other hand, the s of t is obviously closely related to the s of x comma xr, which is appearing in the exponent here. And the question is, what is the relation between them? And the answer is this, is that s of t is equal to s of x comma xr when t is negative, and it's equal to minus s of x comma xr when t is positive. And the result is that it's this main part of the phase that you see here and here. And the only point of this is that it's merely a conceptual one. So you can imagine both of these phases and both of these terms as being due to the same particle doing the same integration and just continuing on around from the upper branch down to the lower branch. These, in some sense, these are the same function if they're thought of as being a function along the orbit instead of as being a function of x. All right. However, there is this phase shift, this pi over 4 here, plus and minus pi over 4, where if I write it in this reflection form, it's really a pi over 2. So, in other words, when the particle gets around to the lower side, the overall phase is really not s of t, but it's s of t minus pi over 2 compared to what it was in the upper branch. Well, what's happening here is that the WKB solution breaks down in a neighborhood of the turning point, so these formulas with these nice s's aren't even valid in this region. So this integration this particle is doing to carry along the phase and this kind of tracing a wave along as it goes, when it gets into this region, it doesn't even make sense to talk about the WKB wave anymore. The whole concept breaks down. But nevertheless, the particle continues on going, and after a while it comes back out again. And when it does, it's now you can continue the integration and you get a wave that's going along here, except there's been a phase shift when it was in this region where the S function didn't make sense as a phase. It accumulated an extra phase of minus pi over 2. As we say, it suffered a phase shift of minus pi over 2 in crossing through the turning point. So this is a basic rule of this in WKB theory, is that the wave function suffers a phase shift of minus pi over 2 in crossing the turning point. Okay. Now, and that minus pi over 2 comes out of this elaborate analysis of area and vary functions. The final rule is really simple. Okay, now, that's all I want to say about the scattering problem. Let me now turn to a more complicated problem, which is an oscillator. Let's suppose we have a potential energy as a function of x, which has some kind of a well. I'm trying to draw it so it's steep on one side and shallow on the other because I don't want to make it a harmonic oscillator. It doesn't have to be a harmonic oscillator. But let's say it's an oscillator like this. Now there's two turning points. There's a left one I'll call XL and a right one I'll call XR, like this. And if we plot the orbit in phase space, x and p, we have the same XL and XR coming down. And then the orbit looks something like this. It kind of does, it can be kind of an egg-shaped object like this. Is an oval shape. I don't want to draw it as an ellipse because in general it's not an ellipse. It's topologically a circle, however, and the part that goes around like this. Now let's take an initial position. I want to first analyze this problem just from an intuitive standpoint. Let's take an initial position on this orbit, and we have a classical particle, and it's going to go around and around. And as it does, let's imagine it carrying out this interval of p dx to accumulate a phase of a wave, which is going along like this. It passes through a turning point, suffers a phase shift of minus pi over 2, and gives a wave that's going back. It passes through a second turning point and suffers a second phase shift of minus pi over 2, and then continues on back, and eventually comes back to where it started from. Now the wave that it's carrying with it, it better be in phase with the wave that it started with, or else you get destructive interference and there's no wave function at all. So what is the total phase? The total phase I'm going around the orbit. Actually, the phase is the integral p dx over h bar. So the total phase I'm going around the orbit, the total phase, the total delta, it's really a total delta phase, change in the phase relative to the initial position is equal to, let me write it better, give it more room here. It's equal to 1 over h bar integral now around the entire loop of p dx. That's the accumulated action function s. But then we have to subtract twice pi over 2 because of the two turning points. Now this total phase had better be an integer multiple of 2 pi. Because as I say, otherwise you will have destructive interference. And so if I bring this is equal to pi, of course, if I bring it over to the other side, multiplied by h bar, what we get is, this is the integral of p dx is equal to n plus 1/2 times 2 pi h bar. And the integral of p dx around the loop is geometrically is the area of the orbit in phase space. And this is a quantization condition. It says that only when the area takes on this special value of a half integer, n plus 1/2 times 2 pi h bar, do we have a phase coherence. This is the semi-classical version of the quantization condition, and one can see that it's really the area of the orbit is quantized. It's quantized in half integer multiples of 2 pi h bar. 2 pi h bar, of course, is Planck's original constant h. Sometimes called a Planck cell. It's the fundamental area of phase space, and in a certain sense, one can say that that every quantum state occupies this fundamental area h of phase space. If I plot the quantized orbits, there's special classical orbits. There's one that has an area of 1/2. That's the beginning one with n equals 0. And then successive orbits have the property that the area of the angular strip separating one orbit from the next is equal to a single Planck cell. So in an oscillator like this, you can imagine the quantized orbits building up like this. Notice that the minimum orbit does not have an area of 0. It has an area of 1/2. This is related to the uncertainty principle, the fact that you couldn't have a particle sitting stationary at the bottom of the well because then the delta P would be infinite. Anyway, this takes care of, this 1/2 takes care of the uncertainty principle for the ground state. All right. So this is an intuitive understanding of what's called the Bohr-Sommerfeld quantization condition for one-dimensional oscillators. There's a quantity in classical mechanics. It's called the action of an orbit. Actually, the word action gets used in several senses in classical mechanics, and they all have dimensions of action, but they're different things. So I'll use different symbols for them. This is called I, and it's just a definition. It's 1 over 2 pi times the area of the orbit. This is how it's applied to the one-dimensional problem. So if I divide both sides of this equation by 2 pi, we can say that for a quantized orbit, the action I, in this sense, is equal to n plus 1/2 times h bar. In fact, let me put an n on it. In K. This is the nth quantized value of the action of the orbit. The action is just proportional to the area, so as the action increases, the orbit is getting bigger and bigger and moving outwards. The way I drew the potential, that means the energy is increasing also. So the energy of the orbit is a function of the action. And classically, you can write a function that gives energy as a function of the action like this. Classically, the action takes on all values. Quantization, of course, occurs only because of quantum mechanics. There's a result in classical mechanics that's worth mentioning, which is the frequency of the motion is actually equal to the derivative of the energy with respect to the action. I won't prove this, but that's an important result. In any case, once the actions are quantized, you can use the classical relation connecting energy and action to find the quantized values of energy. That's to say that E sub n is equal to the classical energy-action relationship evaluated at I(n). That's the energy of the orbit whose area is equal to n plus 1/2 times h. These, then, are the semi-classical or Bohr-Sommerfeld energy eigenvalues for the problem. They're not exact in general, they're only an approximation, but oftentimes it's a very good approximation. Okay. Now, so that is the oscillator treated from an intuitive standpoint by just counting phases. Let me now do it from a more a more sophisticated standpoint. In order to do that, I'm going to need a new set of connection rules, because we need to worry about well, this board takes care of a turning point that looks like this. We need to take care of the other turning point. So let me let me do it on this board. I've already got the connection rules. So I don't need this anymore, and I don't need this anymore. But the connection rules are this. So let's take this situation now where we have a potential energy that's decreasing like potential energy that's decreasing like this, and let's say there's a total energy V like this, and now there's a turning point here that I'll call XL, meaning that it's to the left of the classically allowed region. In fact, let's call this region 3 here as a classically forbidden region in this case, and region 4 is a classically allowed region in this case. Then what we have is that psi in the classically forbidden region 3 of x, let's write this as 1 over the square root of absolute value of momentum times the coefficient of, let's call it c growing, e to the k of x comma xl. Now I'll refer this to the left turning point now, not the right one, over h bar, plus c damp e to the minus k of x comma xl over h bar. And I should say that growing and damped here refer to the behavior of the wave function as you move to the right. So a growing wave function is going up like this. The growing wave function is the one that's allowed by boundary conditions. We want it to go to 0. The damped one is when it's damping coming in like this. It means it's blowing up. If you go backwards, that's the one that's not allowed. But anyway, the general solution is the wave equation looks like this. And then in psi 4, which is a classically allowed region, let's write this as 1 over the square root of p of x. Let's make it a c right e to the I s of x comma xl over h bar plus a c left e to the minus I s of x comma xl over h bar, like that. And those are the gives us the right and left going coefficients. The procedure for finding the connection rules is exactly the same as before. And the algebra is just the same as before, but there's some minus signs and stuff that enter. So there's no point in going through it again. Instead, I'll just summarize what the connection rules are. But I should say here that these are the connection rules in which the let me just draw a picture here. It might be best to make a picture. So here's the XR here. And let me make a new set of connection rules in which the picture looks like this. This is our potential energy here, V of x. Another picture here of V of x. And now the potential energy is going down like this, and here's a turning point for energy E, which is XL. And so then I just need to cite for you the matrices, which if I can dig them up here in my notes. I will do that. We need these notes here. Yes, here's what they are. So what we get is CG, CD is this matrix 1/2, 1/2, minus I. You don't need to copy this down because it's in the notes. CR, CL, I found some errors in the notes, it's all correct. CR, CL, the inverse matrix is 1 I over 2, 1 minus I over 2, CG, CD. And these are the connection rules then in the other direction. So both these are connection rules, but they work at turning points that are either on the right or the left of the classically allowed region. Now, as I say, let's now use this to solve this oscillator problem, which is on this board here. Let's solve it in a somewhat more rigorous manner, instead of just using this intuition about how the particle accumulates phase as it goes around the orbit. So let's do this. Let's draw our potential energy like this. The total energy E. So here's the left turning point. Here's the right turning point. I must have drawn this somewhere else because I remember doing it. Here's the bring these turning points down. Here's the phase picture X and P, and you get an orbit that goes around like that. Let's call these regions 1, 2, and 3. Not the same number that I used before. Here 1 and 3 are classically forbidden, and 2 is classically allowed. And let's write psi in region 1. Let's write it this way: 1 over the square root of the absolute value of P of X times a growing coefficient. I'll call it AG. I'll call the coefficients in these regions A, B, and C. A in this region, B in this region, and C in this region. So let's say A growing e to the k of x comma xl over h bar plus A damped e to the minus k of x comma xl over h bar. Psi in region 2 is going to be 1 over the square root of p of x. And now I'll use the version of the wave function in which the action integrals are referred to the left turning point. This is, I forgot something. A moment ago I was explaining that you get different connection rules if the turning point's on the left. But what I forgot to mention is just like we did in the case of the turning point at the right, it was convenient to introduce phase shifts of pi over 4 into these exponents with the s's in order to make it agree with the phases that are in the standard forms of area and vary functions. Here it turns out I want to put in a minus I pi over 4 on this side, and a plus I pi over 4 on this side, and that's going to be necessary to make these formulas correct. If I don't do that, then there's extra factors of e to the I pi over 4, and this makes those matrices a whole lot messier. All right, now. So here is the psi 2 in this region. This is, let's call it a d coefficient to the right, e to the I over h bar s of x comma xl minus I pi over 4 plus d right e to the minus I over h bar s of x comma xl plus I pi over 4. However, there's another expression for psi 2 that we get by referring the action to the right turning point. There's actually two expressions here because we had two turning points, and in both cases we had formulas to the right and the left. So let's call this dr prime. This is another way of moving to the right, but the action is referred to the right turning point now, and the sign of the pi over 4 is the opposite. Let's call this dr prime, e to the minus I over h bar s evaluated at the right turning point, minus I pi over 4. And then finally, in region 3, let's write this as 1 over, which is a classically forbidden region. Let's write it as 1 over absolute value of p, and let's call this c growing e to the k of x comma xr over h bar plus c damped e to the minus k x comma xr over h bar, like that. And the algebra of doing all this is really a glorified version of what you've done in undergraduate courses where you have square law potentials. This is slightly more complicated. But once you've got the matrices, it's just the algebra working through the matrices. So here, for example, I'll start from the left and move to the right. The boundary conditions in the left are that the coefficient of the damping term of wave function is going down like this has to be 0 because that's the one that's blowing up as x goes to minus infinity. So we have to have AD is equal to 0, and I'll use my eraser to get rid of it. And as far as AG is concerned, the coefficient of the growing term, let's set it equal to 1, which is just an arbitrary normalization. Now then, once we've got that, we can find the coefficients BR and, let's see, this is BR and BL. This is BL prime, right and left. We can get BR and BL by using the upper version of the connection rules. The symbol C's get replaced by A's and B's. But this is going to be VR and VL is going to be that matrix 1 I over 2, 1 minus I over 2, multiplying onto, I'll remind you that A down was equal to 0 and A going was equal to 1. So it's 1, 0. And the result of this is we find that VR equals VL equals 1. So let me just erase them because they're equal to 1. This is now the formula of this first version for psi at location 2. Now these two expressions for the wave function in the classically allowed region 2 have to be equal to each other. There's only one solution there. And moreover, the right traveling wave, the two right traveling waves and the two left traveling waves have to be equal too. So this entire term up above must be equal to the term below, and that allows us to solve for VR prime. Let me show you how this is done. This gives us e to the I over h bar s of x comma xl plus I pi over 4, that's this upper term, is equal to VR prime times e to the I over h bar s of x comma xr, referred to the right turning point. This should have been a minus pi over 4, plus I pi over 4. Now, s of x comma xl, its definition is it's the integral from xl to x of p dx. That can be written as the integral from xl to xr of p dx plus the integral from xr to x of p dx, of which the last term here is s of x comma xr. These two actions measured with relative to the two different turning points are related to one another just by a constant. You change the lower limit, you just add a constant. And what is that constant? It's this integral here. Well, if you look at the p dx, p is a function of x, integrated from the left turning point to the right turning point. It's the area under the top of the curve. So that integral here is actually equal to 1/2 of the area of the orbit. But the area of the orbit is equal to 2 pi times the action, so this is equal to pi times the action I. And so the result is that if I make this a product of two phases like this, e to the minus I pi over 4, then this first phase here is equal to e to the I over h bar times s of x comma xr, which is the right turning point, times e to the I over h bar times pi I. And now you see that this phase here cancels with that phase. That's the x dependence, which had to go away because the VR prime is a constant. And the rest of it is just solving for VR prime. So what we find is that VR prime is equal to, just bring this e to the minus pi over 4 on the other side, and it becomes e to the I pi over h bar times the classical action I minus I pi over 2. In that manner, we determine this coefficient VR prime. Now, as far as VL prime is concerned, it will be the complex conjugate of VR prime because the line above is real, the line below has to be real also. So if you have VL prime is equal to e to the minus I pi capital I over h bar plus I pi over 2. Let me box that because that gives us two more of the coefficients. Now, finally, the only thing left to do is to use the next connection rules for a right turning point to get the coefficients CG and CD. So, gosh, I'm afraid I'll have to erase this just to make room. So what we're going to have then is that now we need to use these connection rules for a turning point on the right. So CG is going to be equal to I times VR prime. I'm using this matrix, but I'm reinterpreting CR and CL as prime VR and VL minus I VL prime And if you look at that, I times dr prime, the I is going to cancel d minus I pi over 2. And so what we get is that this is the cosine of pi I over h bar. And as far as C gamma is concerned, it's 1/2. And now it's going to be this matrix, 1/2 of the sum of the two. So it becomes 1/2, turns it into a cosine. It becomes the cosine. This was actually twice the cosine. Now it turns into a cosine of I pi over h bar, pi I over h bar minus pi over 2. All right. However, the coefficient of the growing solution in this classically forbidden region on the far right must be 0, about boundary conditions. So this we set equal to 0. And so that means that pi I over h bar, which is the angle inside the cosine, has to be equal to pi over 2 or 3 pi over 2 or 5 pi over 2. Those are the places where the cosine is 0, which is the same thing as n plus 1/2 times pi. And if we then multiply this out, what we get is that I is equal to n plus 1/2 times h bar. And that is the quantization condition of the action of the orbit, essentially the area of the orbit, same one we got earlier by using this intuitive rule by the particle accumulating phase as it goes around the orbit. This is a re-derivation of the four Sommerfeld conditions using the connection rules. We get something else too, because if I plug in I equals n plus 1/2 h bar into here, this thing becomes the cosine of n pi, which is equal to minus 1 to n. And so we get an explicit solution for the CD coefficient. The C growing coefficient was 0, so I'll take it out, and then CD is minus 1 to n when we do the quantization. And so, in addition to getting the quantization conditions, this more detailed analysis gives us the benefit of getting the wave functions as well. The wave function in the classically allowed region might be the most interesting one. It's really the second line here, and I can write it this way as twice divided by the square root of p of x times the cosine of s of x comma xl, and then draw to the left turning point over h bar minus pi over 4. And this is actually one of the useful results of WKB theory, is that it gives you the WKB approximation for the wave function of the oscillator in the classically allowed region. In the classically forbidden region 1, it's 1 over the square root of absolute value of p of x e to the minus k of x comma xl. And inside 3, with x is equal to 1 over the square root of absolute value of p of x times e times minus 1 to the n, e to the minus k, this is over h bar, of x comma xr over h bar. And so there's the complete set of solutions in all three regions for this problem, this oscillator. What time is it? Oh, I'm so sorry. I read the watch and I didn't hear the bell. Okay, anyway, at least this is a good starting point. It turns around and comes back. So as it climbs in the gravitational field, of course, its velocity decreases, it's decelerating. That means the momentum is decreasing. And that means the wavelength, which starts out short, gets longer and longer and longer as it comes closer and closer to the turning point. Also, since the velocity is going down, it means the amplitude must be going up, because, as we just have learned, the amplitude goes as 1 over the square root of the velocity. So, just on general WKB grounds, we expect a kind of an envelope that looks like this. Then there's going to be oscillations in here, and as you move further towards the origin, the wavelength gets longer. And finally, what it does is it does something like that. It doesn't go to infinity, but it reaches a maximum near z equals 0. That's the turning point. And then there's some penetration into the classically forbidden region where the classical particle wouldn't go at all, positive z, and you get a decay over here, an exponential decay. Well, this is actually a sketch, not a bad sketch, if I do say so myself, of the area function AIZ, which you can look it up in the books. But this is a way of interpreting what that solution means. Now, as far as the Berry function is concerned, that's the other linearly independent solution, and it also has the same envelope, like this, but the oscillations are 90 degrees out of phase from the area function, so I can't really draw them on the board, but they get longer wavelength as you get closer to z equals 0. And then what happens is in the classically forbidden region, they diverge exponentially. And this is the Berry function, which you would say is the solution that has to be rejected because of boundary conditions for the particle in the gravitational field. But nevertheless, it gives you, again, I say by this physical model, it gives you an idea of what these asymptotic forms mean. And carrying these exact solutions out to large negative z or large positive z for both these functions yields these expressions we have here summarized over here for you. Copy that in the book. All right, so that's the properties of the area and Berry functions. It's not so bad, actually. So now, if I may reveal my board again here, it must be that these WKB solutions, psi 1 and psi 2, which you see here, must be the same 6 coefficients altogether. There's got to be connections amongst these coefficients, which we need to work out. Okay, so how do we do this? Well, before I do that, let me tell you about the area and Berry functions. I'll unfortunately have to cover this up, but if you go to the books on standard functions, special functions, you'll find under the chapter on the area and Berry functions, you'll find these limiting forms for these two functions when z is large and negative or when it's large and positive. And this is just what you get out of the books. I could derive these formulas for you. It's actually not that hard. Take about a lecture or a lecture and a half. But for lack of time, I won't do that. Let's just say we read it out of the books. But what you can recognize is that these are asymptotic forms valid in large and small z. What you can recognize is that there actually are WKB forms. You see, in the classically allowed region, which is z negative, you've got cosine and sine terms. These are real exponentials of two waves going in the two directions. And in the classically forbidden region, you've got growing and ebbing exponentials. So that part's easy to see. In order to understand these formulas, however, let's adopt a physical model in which the potential really is a linear function of position. An example would be, let's say, V of z. Let's say a particle in a gravitational field where the potential is mgz. Then the Schrodinger equation is, of course, minus h bar squared over 2m. And also, let's take the energy equal to 0. Let's do that. So it's minus h bar squared over 2m. You have d squared psi dz squared plus mgz psi equals 0. You may compare that to the area and Berry equations, which is right here. And you see, except for the constants, it's the same equation. So, apart from scaling and constants, the area and Berry functions are the exact solution of the Schrodinger equation for a particle in a gravitational field with a zero energy. Let's look at that problem from the standpoint of classical mechanics, or maybe you might say WKB theory. So here's the z-axis, and so you imagine the particle is climbing in a gravitational field. The total energy is 0, so it reaches a turning point at z equals 0. And as you'd expect, since it's a probability that you can, for an oscillator, a bound state system, you can normalize. And that means the amplitude actually goes as 1 over the distance to the 1/4 power from the turning point itself. But they diverge, and so there's a question about what does the real wave function look like? Does it diverge? No, it doesn't. It's a solution to the Schrodinger equation. I'll show you in a minute what it actually looks like there. But in any case, that's the problem near the turning point. And we fixed it up by inventing yet a third solution, again an approximate solution, which is valid in the immediate neighborhood of the turning point. We do this by approximating the potential by a straight line there. If I draw it in, it looks like this. This is going to be valid at least in some region around the turning point. Here's a series of the potential carried at first order. XR is the turning point. This is just a constant coefficient here. It's the slope of the potential. If you plug it into the Schrodinger equation, it becomes this. It's now a Schrodinger equation naturally with a linear potential, because that's what you replace the real potential by. And as I explained last time, we'll clean this equation up by doing a linear transformation, going from an old variable x over to a new variable z, such that z equals 0 at the turning point. So over here, in this diagram here, this classically allowed region is the one where z is less than 0, and the classically forbidden region is one where z is positive, and the turning point itself is z equals 0. And the constant a of the transformation, we choose to clean up the physical constants in the Schrodinger equation, and this turns out to be the choice that does it. And if you do it, you end up with a differential equation for the wave function in the neighborhood of the turning point, which does not involve any of the constants at all. It's now a completely dimensionless form. And this, as I explained last time, is the standard equation for the area and vary function, which are special functions. These are the two linearly independent solutions of this equation. And so in the neighborhood of the turning point, the wave function is now a linear combination with a coefficient area and a coefficient vary of these two functions, area and vary. And as a result, we now have three different regions with three solutions. In each solution, there's two pairs of coefficients. So there has to be a connection. Now, together, the C right and C left in the classically allowed region, with the C growing and C damped in the classically forbidden region. But as I explained last time, you can't do that just by bringing in both solutions up to the turning point, because there's a certain region around the turning point where both these solutions become invalid. Let me elaborate on that breakdown near the turning point just a little bit. I'll cover this up and we'll bring it back again. As you'll recall, the amplitude is the amplitude squared times the velocity is the same as the amplitude squared is the same as the classical probability density, which is proportional to 1 over the velocity v. This gives the amplitude is proportional to 1 over the square root of the velocity, which is proportional to 1 over the square root of the momentum, which is how it's appearing in our formulas. In any case, if we have a situation like I sketched a moment ago, where we've got a turning point that goes up like this, here's an energy E, then if we plot the velocity, you see the velocity is positive here, but then it goes to 0 as you come to the turning point. So 1 over the velocity, or 1 over the square root of the velocity, is going to be a function that's going to do this. It's going to diverge at the turning point. In fact, you can see that the divergence goes as, well, the divergence goes, the amplitude A goes as 1 over the square root of the velocity, goes to infinity there. Also, as I explained last time, this implies that the conditions of the WKB approximation, which is that the wavelength should be much less than scaling, breaks down there, because near the turning point, lambda actually goes to infinity, since the momentum is going to 0. Okay, so no wonder the WKB solutions don't work there. But there's you might say the nominal WKB solution blows up at the turning point. It does also in the classically forbidden region, because there's a 1 over square root of momentum there as well, but they both blow up at the same place. Now you might ask, what does the real solution do? What does the real quantum mechanics do? Well, by the way, the classical probability is a meaningful quantity classically, and it does diverge there. It diverges as 1 over the square root of the distance from the turning point, which means that the integral of the classical probability is finite. Let me remind you where we are. We're in the thick of a bunch of stuff here, so I've summarized it on the board. In the first place, I can use a pointer. We're considering a case in which there is a potential that's rising as you go to the right, so that there's a classically allowed region to the left of the turning point and a classically forbidden region, CFR, to the right. These are also labeled 1 and 2. XR here is the turning point itself, and the R just means that this turning point is to the right of the classically allowed region. Down here is the face of the picture. Then, using the WKB solutions that we've worked out so far, in the classically allowed region, which is region number 1, the momentum function is defined like this. It's a real function, real and positive function. The action function, or the function S, which appears in the exponents, also called an action, is basically the integral of p dx. There is a question of the lower limit, which, as I pointed out last time, is related to the phase convention of the wave function. So you can set it for anything for now. We'll worry about phase conventions later. The most obvious point to choose is the turning point itself. And that's what I've done in this integral here. And I've called it S of x comma xr to indicate what the lower limit of integration is, to be explicit about that. In any case, using a linear combination of the forward and backward, or right and left going solutions, it's either the IS and either minus IS, or the H bar, with coefficients C right and C left. This gives us a general linear combination in the classically allowed region. Now, in the classically forbidden region, which is also labeled number 2 here, the momentum is purely imaginary. If I take its absolute value, it just means to drop the I and just deal with this positive square root. And we define a modified action we call K, which is the integral of this square root dx, absolute value of p of x dx. And again, the lower limit is based on, it really determines normalization in phase of the wave function. And just to make it definite, so we have a definite number, we'll use, again, the right turning point xr here as the lower limit. And then we form a linear combination with the 2 WKB solutions, a growing one and a damping one with coefficients C growing and C damping. And so we have these 2 solutions in these 2 different regions, and in each region there's 2 arbitrary coefficients. Now the problem is to connect